Oops, sorry. You guys see the objective and you see the constraint. Okay, for the constraint, do we have to do some work beforehand?
Yes.
Yeah, let's subtract 20, right? Move the 20 to the left-hand side. So this is the same as x plus y minus 20 equals 0. Okay. So if we use Lagrange multiplier, we have to construct function f of x, y, including multiplier lambda. So that would be your objective xy minus lambda times the constraint. This is our g of xy. So x plus y minus 20. And then it's straightforward, right? Take 3 partial derivative, fx, fy, f lambda, and set each of those equal to 0. What's fx?
X minus, it's just X.
Well, is it x?
No, it's Y.
Y
Yes, Y, sorry.
minus. And then there's another partial x. Remember, here's x, right? So if you distribute the lambda, you're going to have lambda x. So when you take derivative of this lambda x with respect to x, you should have a lambda, right? So y minus lambda equals 0 for partial x. For partial y, you're going to treat y as the variable. Therefore, we should have x minus, same thing here, you have lambda y, whose derivative will be lambda, correct? F lambda is derivative of lambda, so that's going to be a negative x plus y minus 20 equals 0, right? This is a pretty easy case here. We can tell that from equation 1 and equation 2, x equals lambda and y equals lambda. So y equals lambda, x equals lambda, right? Last time we said the best way for us to solve the system is to eliminate lambda from equation 1 and 2. So you can get some relationship between x and y. And then just along with equation 3, you can get x and y's, right? So in these two, it's obvious that we can say y is the same as x because they both equals lambda, right? Then you can simply plug this into equation 3. Equation 3, you can just ignore this negative sign in front because right-hand side is 0. If I plug this into equation 3, I have x plus y, which I can say that's 2x minus 20 equals 0, right? So x would just be 10. When x equals to 10, y would be 10 as well. Good? Okay, and that's the only solution we get, right, from this Lagrange multiply method. So this x and y would give us the optimized value, okay, optimized value. So a of 10, 10, the function a at 10, 10 would be 100. And that should be the maximized value. Okay? All right, any questions? This is pretty straightforward, right? You recognize the objective function, recognize the constraint, use those to form a function including the Lagrange multiplier. Let's see the solution. I've listed the solution over here as well. First, we'll note this x plus y equals 20 is equivalent to x plus y minus 20 equals 0. New function will be this. And then you find a partial derivative and set each one equal to 0. Okay, and you can see x equals lambda equals y. Therefore, we can get x equals 10, y equals 10, therefore the maximum value must be occurring at 10, 10, and the value will be 100. Okay. All right, lastly, let's revisit the example 4 in 12.8. Do you guys still recall this?
Mm-hmm.
The global maximum and global minimum, okay, for a function on a closed set, right? Closed set S. Closed set S here. Closed set S. The set S is actually closed, which means it includes the boundary and the inside, okay? And last time we took a lot of time solving the extreme values, solving the possible extreme values on the boundary, right, on the boundary. Okay, let me see. Okay, so last time we investigate like inside of S and on the boundary. Inside of S, I think we figure out one extreme value. If you don't mind, let me just pull up the slide from last time real quick. Okay, so it was here. So inside of S, we figure out F at 3, 4, we have extreme value, which is negative 18. You guys see this? Oh, sorry.
Yeah.
Can you see my screen? Is my screen sharing paused?
Your screen's on example 3.
Okay, example 3. Let me pull up here. Okay, reshare. So share. Okay, do you see this now?
Yeah.
Okay, this is where we did last time in section 12.8 when we are not introducing, when we don't know the Lagrange multiplier. So at that time, we know inside of S, you can use the second partials test to find a possible min, right? Local min. We have F of 3, 4 equals negative 18, right? Negative 18. And we spent lots of time finding the possible extreme value on the boundary, Recall this? Now, right? Okay, so I'm going to copy this conclusion over there because inside of S, that's easy to solve, right? So let me get 12.9. I think I have to reshare again. Okay, so let's continue here. From current slide. So F of 3, 4 equals negative 18. That's inside of S. Okay, inside of S. This is by second partial, right? Last. Okay, so on the boundary, so that last time it was pretty long. This time let's try Lagrange multiplier method now. Okay. So let's use another method this time to treat the points on the boundary because we need to consider both, right? So this time it's like trying to find maximize or minimize the function f of xy equals x squared minus 6x plus y squared minus 8y plus 7. That's a projective function. Subject to on the boundary. Okay, on the boundary, so we are looking at strictly equal to 1, right? X squared plus y squared equals 1. Which is equivalent to say x squared plus y squared minus 1 equals 0. Is that good? Okay, so then the Lagrange, if we use Lagrange multiplier, we have f of xy lambda would be x squared minus 6x plus y squared minus 8y plus 7 minus lambda times this constraint function, x squared plus y squared minus 1. Okay, so then we just do 3 partials. These are all polynomials, so it's easy to take partial derivative. Fx would be 2x minus 6, and over here you have minus 2x lambda, right? Partial y would be 2y minus 8 minus 2y lambda equals 0. Partial lambda would just be negative x squared plus y squared minus 1 equal to 0. This is equation 1, equation 2, and equation 3. Good so far? All right, so we're going to first of all focus on equation 1 and 2 again. Okay. Let's see, we can eliminate lambda. Okay. In the similar way, let's isolate the lambda term from everything else. So I'm going to move 2x lambda to the right. I'm going to move 2y lambda to the right. So I'm having 2x minus 6 equals 2x lambda, and 2y minus 8 equals 2y lambda, right? This is equation 4 and equation 5. Good? And last time we mentioned one way to eliminate the lambda very quickly. We just need to do one operation about these two equations. What is that operation? You guys recall? Division. Yes, just divide these two equations, right? So if I do division, let me keep doing it here. So I do 4 divided by 5. And at the same time, you guys can see there are a bunch of 2's, right? 2, 6, 2, 2, 8, 2. You can reduce everything by 2. So I'm getting x minus 3 divided by y minus 4. I've already divided everything by 2. Equals x lambda divided by y lambda. So that's just x over y. Is that good? Okay. So then I can do cross multiply, right? Cross multiply. I'm having y times x minus 3 equals x times y minus 4. Which tells you xy minus 3y equals xy minus 4x. Okay, obviously, can we cancel xy both sides?
Yes.
Yep, xy could be canceled both sides. Let me see where my pen. Okay. So xy could be canceled, and you can cancel negative sign both sides, right? So that tells us 4y equals to 3x, which tells you y will just be 4 over 3x. So y is 4/3 of x, right? Okay, that's great. So we know the relationship between y and x. Okay, y is 4/3 of x. So therefore, we're going to plug this into equation 3, because equation 3 is only about x and y's, right? I'm going to say into equation 3, I have x squared plus y, which is y squared, so at 16 over 9, x squared minus 1 equals 0. Is that good? Okay, so you can combine these two x squared term, right? It's 1 plus 16 over 9, so that's 25 over 9 x squared equals, the negative 1 could be moved to the other side, positive 1. Which tell us x squared would be the reciprocal of 25 over 9. So it's 9 over 25. Right? So there are two options of x. X could be 3/5, or x could be negative 3/5, right? y would be 4/3 of x. So you can plug that in. So y would be 4/3, so it'd be 4/5. Or y could be negative 4/5. Right? So in this method, you can get these sort of critical points very easily by using Lagrange multiplier method. Last time we spent lots of time by using the trig substitution, right? You have to use the theta, you have to take the first order derivative, you have to consider what's the tangent value, and by using right triangle, you have to figure out a sine and cosine value. That's pretty complicated. If you know trig well, that should be fine, but if trig is not your strong point, probably that's going to be a little bit struggling. But if you use the Lagrange multiplier method for this question, you don't even need to know about trig, right? Because everything is just polynomial here. So just use the objective function, subtract lambda times the constraint, and just solve the system of equation, and you can still get the same amount of xy. Okay? So I'm just putting this as an alternative method, which might be better compared to what we did previously. Okay, might be a better method for solving the extreme value on the boundary here. Right? Is there any question for this problem, folks?
Hey, Dr. Wu.
Yes.
So
yes,
the fourth fifths came from plugging 3/5 into the third equation?
You can do third equation. Of course, you can do that. Or you can just do this. Remember here?
Oh, okay, yeah, I see.
This will be quicker, right? Because you know y has to be 4/3 of x. Right? So that gives you a more stricter relationship between x and y's.
Okay, I see.
Right?
Thank you.
So what I'm saying here is in this method, it might be easier to find x and y's compared to the trig substitution. Okay? So Lagrange multiplier method is a very good method when you have those constraints with equal sign in it. Okay, has to be strictly equal to 1, right? Equals 1. So your constraint function could be easily obtained. All right, so that finishes the section 12.9, which is the last section in chapter 12. Okay. Did you guys get my email yesterday about the test 3 posted on my courses?
Yes.
Okay, so the test 3 is take home and it's due next week. I've already put the due date on my courses. It's all about chapter 12. Okay, so all the materials is about chapter 12. This Lagrange multiply method will also be tested in the take-home test. So if you have any question, you can refer to these PowerPoints that I've uploaded on my courses. Okay, let me exit this and keep my ink annotation. All right, and then once we finish chapter 12, we're gonna go away, and then let me reshare this. We go to the new chapter, which is chapter 13, talks about double integrals. Okay, double integrals. Double integrals are the ones that we'll be focusing a lot in this chapter. Beginning. The first section, you guys can see my slides, right?
Yes.
Okay. The first section introduces the idea of double integrals over rectangles, okay, which means it's over a rectangular region. Okay, rectangular region. Our objectives is, first of all, understand how can we use a double integral to present the volume of a solid region and use the properties of double integrals. And you see a lot of similarities because they're very similar to our just single integral. There are a lot of properties that's pretty similar to our single integrals that we know. First of all, let's introduce double integrals and a volume of a solid region. Okay, so this needs to be related to come back to the one concept that we talked about in Calculus 1, which is Riemann sum. Okay, Riemann sum. Riemann sum, does this graph look familiar to you guys?
Like the function of the graph or just the graph in general?
The graph in general?
Yeah.
Okay, so this is this is a graph of Riemann sum, right? Riemann sum. Okay, in this Riemann sum, why do we need to use this Riemann sum? What are we calculating, if you remember from Calculus 1?
The area between the x-axis and the curve.
Yes, so we're trying to use the Riemann sum to estimate this area, right? Which is the area between your curve and the x-axis from A to B, right? From A to B. And our rationale is a lot of times these areas are not of regular shape that you can use formula for. Therefore, instead of looking at those irregular shape, we're going to introduce a bunch of rectangles whose area is easy to compute, right? Whose area. So typically what you do is suppose the area, the region starts, the interval starts at A, ends at B. We're going to have certain partition of this interval, A to B. Let me move to the next slide. Okay. So you're going to have a certain partition of this interval. So partition could be P, sometimes use delta, okay, of the interval A, B, right, into subintervals. The subinterval could be equal length or not equal, so unequal length. In this graph that you see here, they are sort of equal length, so that's easier to compute. But a lot of, in general, you don't have to have equal length. And suppose this is the one subinterval, and then you just take a point, right? And then you pick a representative point, x, k star, for the subinterval. Subinterval for the kth subinterval, right? Kth subinterval. And then you can construct a rectangle by using the function value. This will be the height, and this will be the base. Okay, so therefore you get this rectangle, compute its area. And we just repeat this process from the first rectangle to the last rectangle, right? And then you add up all the areas. So in general, how do we calculate the Riemann sum? We call this Riemann sum.
You add the rectangles together.
So Riemann sum, according to this partition, will be the sigma, right, which is the sum of area of those individual rectangles, right? So I goes from 1 to, say, n. This is the last rectangle. And each area of rectangle is easy to compute. It would be base times the height. So the base will just be the length of the subinterval, right? Which is delta xi, if you guys recall. It's the change of the x amount. And function value would be just the height, right? So the height will be f of xi star, okay, the representative point. So this is a Riemann sum. And how did we relate to Riemann sum to integrals? How do we further make the connection between Riemann sum and integrals? We know integral, right? So this area, the actual area, could be represented by using integral. So integral is from A to B, right? So A to B, function is f of x dx. So this integral is basically if you force this delta xk to be very small. If you have very narrow strips, right? Very narrow strips. This is one limit of the partition of this partition going to very small, going to almost 0, then each of these delta xi will almost approach 0, right? Taking that limit. So limit of sum of delta xi, f of xi star. So I goes from 1 to n. So this is how you relate integral to limit of the Riemann sum if the limit exists, right? So in general, I would just say integral is just the limit of Riemann sum when the corresponding partition goes to 0, right? The magnitude of the partition goes to 0. Recall this? Folks. Okay, so that is one, I mean, this is two-dimensional, right? This is 2D for y equals f of x. Okay, if there's only one single variable, the corresponding Riemann sum will just be looking like that. And the same idea could be extended to 3D. Now, extend this to 3D for z equals f of x, y. So in this section, we'll use a similar process, which means partition, right? First of all, get partition and choose representative point, and get this the corresponding quantity, whether it's area or volume, depending on what you're calculating, and then find the sum of those quantity, right? So similar process to define the double integral of a function of two variables over a rectangular region in a plane. Okay, let's look at this graph. Consider a continuous function f, okay, this is a continuous function, such that the z is greater than or equal 0 for all the xy in the region R. This is region R here, region R, okay, in the xy plane. The goal is to find the volume of the solid region lying between the surface given by the z and the xy plane. So this is the region R, okay, so region R is here, okay, and this is the surface which is above this xy plane, right, above the x plane. So you can tell there is certain volume solids that you can construct. Would like to find the volume. Is that clear, guys?
Yes.
Okay. So pretty similar. The first thing what we need to do is we need to get a partition, okay, partition of the region. So last time we're looking at an interval AB and we just get a partition of subintervals, right? And this time we have both x and y. Okay, here's x. Here's y. Okay, so you just get the partition on the x direction and you get a partition on the y direction. Okay. Therefore, you get a bunch of rectangles constructed as shown in here, right? Rectangles. Is that clear?
Mm-hmm.
So the rectangles lying entirely within the region R would form an inner partition. So the partition, which is the step, the delta, or which is also, you can say P, partition P, whose norm, okay, which is the magnitude, is defined as the length of the longest diagonal of the nth rectangle. So this will be its norm. Okay. All right, so we finished the partition into rectangular, small rectangular blocks. Next, we'll be picking representative point from each partition, right? Mm-hmm. Okay, so suppose this is a specific rectangle, I can just pick a point as its representative point. It doesn't matter where the point is. It could be in the left corner, it could be in the right corner, it could be anywhere inside of this rectangle or on the boundary. Okay. As long as you call this as a representative point. Okay. So suppose the representative point will be xi, y of I. This is the representative point you found. Okay. So then we're going to use this representative point and go up to the surface, right? Go up to the surface. Okay, and you can construct a small prism, right? Okay, prism, or you can just imagine this as a long box, right? It's a pretty high box. Okay. Can you guys see this?
Yes.
Okay. So this is a rectangular prism, which has a base. A base will just be a rectangle, as we mentioned, and whose height will be the function value. So height is the same, and the base will be a rectangle looking like this. Okay. So we have here these two identities. Identify. Height of this prism will be the function value, which is similar to what we had in two-dimensional. Area of the I rectangle, let's just use delta AS of I, okay? Because this is the I rectangle. So very easy to find. We can find the volume of this I prism, right? So the volume of the I prism will be the base times height. So base of the rectangle, which is delta AI, times the height, which is the function value. Is that clear?
Wait, to find the volume, you need to do base times height?
Yeah, because this shape is pretty easy to find its volume, right? It's a kind of like a long box. So think about the volume. Volume would be area of the base times the height.
Oh, okay.
Right.
I thought it was just the length.
Oh, I'm sorry. Yeah, I should say area of the base, right? Area of the base times the height.
Okay, that makes sense. Yeah.
Delta A sub I times function at x I y sub I. Okay. So then we can get the Riemann sum, right? So Riemann sum will just be adding up all those. Okay. So Riemann sum will just be summation of v's of I, right? I have, say, like n. If I have like n prisms, then I just add up all their volumes. So sigma of v's of I will be summation sigma of area of the base times the height, right? Which you can tell from this graph here. You just go ahead and construct the corresponding prism, okay, for all those rectangles you have on the region R. Then each one you can find a small prism like this, right? Each one you can find a small prism, and its volume will be area of the base and times the height. So I just add them up. That's going to be the Riemann sum. Is everything good, folks? Okay, and obviously this Riemann sum could be getting better if I have very small meshes, right? If I have a very small rectangles on the region R. So this approximation can be improved by tightening the mesh, okay? Making them very small of the grid to form smaller and smaller rectangles over the region R, okay? Which means I'm going to choose the limit, right? The limit when the norm of this partition is heading to 0, tightening the mesh. Okay. So then we just do the volume. Volume will be the limit of tightening those mesh of this Riemann sum. Okay. So volume is just the limit, delta, at a norm of delta approaching 0, a Riemann sum according to this partition. If the limit, again, exists, right? Is that good?
Yes.
Okay. All right, so if this limit exists, then this talks about the value, and therefore we can introduce the definition of the double integral. Okay, double integral. So the limit of sigma sign would just transform into this double integral sign, the double integral. And then the function f of xy is still the integrand. And the delta a is the same as the differential of a. You see the correspondence? So double integral sign, function f of xy, delta a converts to dA. dA. So this is the definition of double integral. Okay. Double integral basically just talked about the value of the solid that is between your surface and xy plane. So if f is defined on a closed bounded region R in the xy plane, then the double integral of f over R is defined as double integral sign over R, f of xy, dA, which is the same as limit of the Riemann sum. Okay, so this is so-called double integral. So the one that we had before can also be referred as a single integral because it has one single integral sign. Okay. Is everything good so far? Any questions? Okay. All right, so next thing is just some properties of double integrals, and they are pretty similar to the properties of single integrals. The first one, okay, so let f and g be continuous functions over a closed bounded region R, and c is a scalar, okay, a scalar. The first one says double integral of a scalar times a function f of xy could be, c could be pulled out, right? Scalar could be pulled out, the integral sign. That's easy, right? Scalar multiplication. Second property says double integral of f plus minus g would be the double integral plus minus double integral, which we can say this as double integral of the sum or difference is the same as sum difference of the double integrals, right? Do we have this similar property in single integral? Folks, if I just remove one of the integral sign, does that still work?
Yes.
Yeah, it still works, right? Item 3 says, if my integrand is greater than or equal to 0, then this double integral will be greater than or equal to 0. Okay, does that make sense to you? And how do you explain?
Yeah, that makes sense, yeah.
Okay, you can say the surface, right? This is surface. The surface is completely above xy plane, right? Surface is above xy plane, therefore, of course, the volume of the solid has to be greater than or equal to 0, right? Surface z equals f of xy. Okay. It's just like the graph that we have seen before, like this graph. The surface is above, okay, xy plane, so the volume of solid, of course, is going to be positive, right, in general. Item 4, which is the comparison property. Comparison property. Comparison property says if I have two surfaces, right, if f is greater than or equal to g, then the double integral of f would be greater than or equal to double integral of g. How do we explain this?
The volume of function f of x is greater than g of x.
I can say I have two surfaces, right? One is function f. Okay, let me do this just very quickly. I have one is function f, and then the other one is function g, right? G is lower. Here is f. Okay. So of course, if you construct a solid, right, over the same region, the volume of F, right, the solid under F would be bigger than the volume of the solid under G, right? Okay, so that's comparison property. Lastly, we have double integral of F over region R equals to double integral of F over region R1 plus double integral of F over region R2, where R is the union of two non-overlapping subregion R1 and R2. Did we have similar property like this in single integral? By the way, this is called additive property. Okay, I'll write something similar that you can recognize in single integral. So if I have integral a, b, a function f x dx plus integral b, c, f of x dx, what can we say?
That's equal to the integral of
A,
x.
c, right? Integral a to c, f of x dx. Because you can add these two intervals, right? AB plus BC interval will just be AC interval. So same thing here. If you have region R1, add region R2 would be region R. Then I can add the double integrals. Okay. I have the next slide here. So this is region R1, this is region R2, and if you add them both, which is called union, right? The union of R1, R2 would be region R. So if you put this as the whole as region R, then double integral over R would be double integral over R1 plus double integral over R2. Is that clear? Very easy to understand, right? Okay, so all of these are pretty just simple concept. Next note is something that you use a lot. Okay. Double integral of constant k here. If k is a constant, then double integral of constant k dA. Of course, I can pull the k out, right? Equals k double integral of 1 dA. Okay, and we're going to say this part is the same as area of R. Why? Can you use a graph to show this? Okay, don't forget that when we introduce the double integral, it's the idea of the volume of the solid, right? So in this case, the function f of xy, which is the integrand, will be 1. Correct?
Yes.
What does the graph of 1 look like? What is this graph? What kind of surface is this?
It's just a plane.
Yeah, it's a flat plane, right? It's a flat plane, horizontal to, parallel to xy plane. So here, suppose here is z equals 1. So we're going to have a plane like this, right? So if I have a region R on the xy plane here, suppose this is a region R over the xy plane, right? Region R is in the xy plane. Can you construct a solid? Can you sort of see what does the graph would be looking like? So just simply project up there, right? Project up there, project up there, over here. Then don't we just get a box? Right? This is gonna be the corresponding solid, right? Which is double integral of 1 dA over R. So it's the volume of this box, right? How do we calculate the volume of this box?
Area of the base times height.
So area of the base, which is area of the region R, times the height. What is the height here?
K.
Okay, is already out. I'm looking at this. I'm only looking at this double integral here.
Oh,
Double integral of 1 dA. So what's the height here?
1.
Yeah, height would just be 1, right? Because z is only 1. Make sense?
Yes, no, it does.
Okay, so this part would just be area of R. So that's why I'm saying this double integral of 1 dA is area of region R. Make sense?
Mm-hmm.
Okay, so next time if you see any constant as the integrand, you can just pull the constant k out and then you do area of region R. Okay, area of region R. Alrighty, let's do 2 exercises and then we're done today. Okay. Example 1, let's evaluate this integral, a double integral of f of xy dA over region R if f of xy is a piecewise function. Okay, it has 2 pieces. The function value equals -1 if x is between 1 and 4, y is between 0 and 1. The function equals to 2 if x is between 1 and 4, y is between 1 and 2. So we're doing integral of f of xy dA over the region R, right?
Mm-hmm.
The region R will be based on what is the corresponding given domain. So there are 2 parts of this given domain, right? Can we sketch this region R in xy plane? Of course, that should be easy, just on xy, right?
Mm-hmm.
So one part is between 1 and a 4, so 1 and a 4, y between 0 and a 1. Okay. This is the first part when x is between 1 and 4, y between 0 and 1. Is that good?
Mm-hmm.
Let's call this R1. R1. The other part is for x between 1 and a 4, y between 1 and 2. So y between 1 and 2, x is still between 1 and 4. So can keep building another part. Okay. This will be my R2. Right?
Mm-hmm.
And R1 and R2 are not overlapping. Okay, they don't have any intersection other than this boundary, right? So I can say the region R will be R1 union R2. Here will be R2. Is that good?
Mm-hmm.
So if I want to do double integral of this region R, can I use the additive property to split this into, okay, they add up to be R, right? So I can use additive property. I can say this will be double integral over R1 and plus double integral over R2. Good.
Mm-hmm.
Additive property. So R split into R1 and R2. Okay, next let's look at these 2 double integrals. So R1 is, the function has this constant amount. So that'd be double integral over R1. Function value is -1 dA, right?
Mm-hmm.
Plus double integral over R2, function value over R2, this time function value would be constant 2 dA. Okay, can we use the note that we just put over here in the previous slide? Double integral of k dA will just be constant k times area of region R.
Mm-hmm.
Right? So see, here's a K. So this would be K times area of R1 plus the second K area of R2. Okay?
Mm-hmm.
What about area of R1? What do we have here for area of R1? Should that be easy?
Yes, it's 4.
Well, this be length times width, right?
Mm.
Width times length. 4 minus 3. Don't forget about it. This starts at 1. Okay.
Oh, yes, it's 3.
3 times 1, right? So 3 times 1. Area of R2 is pretty much the same, right? 3 times 1. So it's -3 plus 6. Therefore, this double integral would be 3. Okay? Is that clear?
Mm-hmm.
If you want to sketch the graph in 3D, okay, for this case, you can also take a direct look at what they were talking about here. So if I put this in 3-dimensional, I can just go ahead and sketch the function. Okay, so the function equals -1, which will be under xy plane, right? The first piece is when x is between 1 and 4. So 1 and 4, between 1 and 4, y between 0 and 1. So 0 and 1. So for this area, okay, for this area, you have function value being -1. So we're going to have basically, can you guys sort of imagine you're going to have a box going down, right? Because this is the sort of the base, and then the height will be -1, so it's going down. So the first solid will be completely under xy plane,
Mm-hmm.
right? Okay, this is the first solid. The second solid has the function value be 2, so height will be 2, and then it is over the region between 1, 4, okay, 1, 4, and 1, 2. So 1, 2 is here. 1, 2, and this time height will be 2, so you're going to go up for 2. You'll have a second solid, which is above xy plane. First solid is under xy plane. So if I calculate the volume, the first volume should be negative because it's completely under xy plane. The second volume should be positive because it's completely above the xy plane. Make sense?
Mm-hmm.
Mm-hmm. So you would have -3 for the first double integral plus +6 for the second double integral. All right.
Mm-hmm.
Okay, so this is if you look at it in 3D. Okay, I think look at it in 2D was probably easier to sketch. Okay, and then you can use that conclusion that we have put in note. All right, the last example
I have a
here.
question, Dr. Wu.
Yes,
So is
Donovan.
that 3 cubic
Hold on a
units?
minute. Oh, the first
So
one?
it's a volume, isn't it? The answer is a volume.
Okay, yeah. Okay. Oh, I should say this. Okay. Double integral equals to signed volume. So let me correct what I just said. For the first of all, are you talking about the first solid?
I'm talking about the answer we get.
Oh, you're talking about the entire, right? The entire
Yeah.
solid. Yes. If you look at the entire solid, it's signed volume, which means this is a positive part, this is negative. The signed volume would be 3.
Okay.
Mm-hmm. Yeah, because you have some part which is above xy plane,
Yep.
some part which is below xy plane.
And
Kind of
so
like if you remember in calculus 1, right? You have a curve like this, then some area is considered to be positive, some area is considered to be negative,
And
right?
does
You would
the
cancel
three
some.
does the 3 have units, or is it just 3?
Depends on what unit you're given. Here we don't have
Okay.
units.
Okay.
You can just call like a unit cube, whatever. Okay,
Okay.
yeah. All right, the last question should be pretty straightforward for you guys. Okay, here double integral of f over region R is 3. Double integral of g over region R is 5. Notice that they are over the same region R. Okay, let's evaluate these two double integrals. Double integral is f minus g over region R, and double integral of 2f plus 5g over region R. Should that be easy?
Yes.
Okay, the first one will just be double integral of the difference will be the difference of integral, right? Will be a difference of f minus integral of g dA over the same region R. And we know these two amount, right? The first amount is 3. Second amount is 5, so I have 3 minus 5, which is -2. Okay? Question 2, integral of 2f plus 5g. We know this. If this is in single integral, you know, you can pull out the 2, so it'd be 2 double integral of f dA. You can pull out 5 plus 5 double integral of g dA, which would be 2 times double integral of f dA, that's 3, plus 5 times double integral of g dA, so that is 5. Therefore, I have 6 plus 25, which is 31. Right? Okay, and then lastly, I want to mention that some of you guys probably remember the name. Okay, for the property 1 and 2 over here, you can pull out the scalar c, you can add or subtract 2 double integrals. Combine, this is called linearity. The linearity property of double integrals. Okay. Integrals has linearity. Okay. Which is the one that we have used here. Pull out the 2 and retain the operational sign. Okay, very lastly, I just want to kind of rephrase what we just discussed. The volume of a solid region, volume. If function f is integrable over a plane region R and a function is greater than or equal to 0 for all x, y, then the volume of the solid region that lies above R and below the graph of f is integral of f d function f dA over region R. This is kind of like what we started our discussion of the double integral. Okay, so a quick reminder, volume can be computed by using double integral. Okay, also, what about single integral? What does single integral tells you?
Area
Yeah, suppose the integral of f of x dx over an interval I, what does that give us? What quantity does this represent?
area.
Yes, so suppose this is interval I, here's f of x, y, f of x, then the single integral basically tells you area, right? So you can tell that area would be single integral and volume will be double integral. The quantity keeps increasing, the corresponding size. Okay? Any question about this?
No.
All right, that's all. That's all for this section. 13.1 is pretty short. Okay, so don't forget to do your test 3. I'm also going to assign some questions for this new section as well. Okay, so check out my courses.
When do you want the test turned in? You said next week?
I think next week. Yeah, I forgot exactly. I think it's next Wednesday. Did I say next Wednesday? It's on the instruction. Yeah.
Okay.
I believe it's next Wednesday, if I remember correctly. Okay, next Wednesday by 5 p.m.
Okay.
Yeah.
I also have a question, Dr. Wu.
Yes.
So for the two integrals, do both of them always have the same upper and lower limit? I mean,
No. You can see all kinds of upper and lower limits. We'll talk about the specifics once starting next section. Okay.
Okay.
You'll see the actual double integrals and how do we compute them. Okay.
Yeah. And
All right.
also, one of my classes yesterday, we were discussing triple integrals, but like, I'm not
Yeah.
sure visually what that represents.
Triple integrals, it's hard to show the specific quantity, but if you have triple integral of 1, we can show that. Like when it's triple integral, when the integrand happens to be 1, then it goes down to volume.
Okay.
Yep. We'll talk about triple integral in the last section, I think. Yeah, of this chapter. So you'll see triple integral.
Okay.
But if you know double integral, then you can extend the idea to triple integral. All right.
Okay, thanks.
No problem. Any other questions, guys? If not, then I'm going to just stop the meeting and now, okay? I'm going to see you guys on Friday.